All right, for our third and final example on washer-based solids of revolution, we're going to find the volume of the solid generated by revolving the region bounded by these three curves: y equals x squared plus 2, y equals negative x plus 4, and y equals 6. And we're going to revolve those around the x-axis. So I'm going to again make a quick sketch. And we've got our parabola, y equals x squared plus 2. And we've got this line, y equals negative x plus 4. And we've got our line, y equals 6. We graph all of those. And we end up with this region in here that's bounded by all three of those curves. And that's what we're going to revolve around the x-axis. Now what makes this example different from all the examples that we've had before is that if you look at this region as we go from left to right, it starts out with the line y equals 6 and the line y equals negative x plus 4 as the outer and inner boundaries of the region. But we get across here to right where this red line is, and then the lower boundary of the region changes. It changes from being the line y equals negative x plus 4 to being the parabola y equals x squared plus 2. And so in order to find the volume here going around the x-axis, it's actually going to require for us two integral expressions. One to get the volume of the portion of the solid to the left of that red line, and one to get the volume of the solid for the portion of the region to the right of that red line. And so we start off by writing our first integral. We're going to have pi times the integral of the outer boundary squared, which is y equals 6, minus the inner boundary squared, which is the negative x plus 4. We'll worry about the limits of integration on that in a second. And then we have a second integral, which is going to be represented by pi times the integral from somewhere to somewhere, of the outer boundary squared minus the inner boundary, which now is x squared plus 2. And we're going to take those two integrals. The first one gets the volume of the solid generated to the left of the red line, and the second one gets the volume of the solid generated to the right of the red line. And so we're going to add those two together to get the total volume of the solid. And now I just need my limits of integration. Since we're doing this in terms of x, we want the x coordinates of these intersection points. This leftmost intersection point happens at x equals negative 2. So that's going to be my lower limit of integration for the first one. And this rightmost point of intersection happens at x equals positive 2. So that's going to be my upper limit for my second integral. And now I just need to know where y equals x squared plus 2 and y equals negative x plus 4 intersect. Now I can go ahead and set those two equal to one another and figure out where that intersection point is. Or I can just go ahead and graph those two curves. So y equals x squared plus 2 and y equals negative x plus 4. Missed a negative sign. And I'm going to go ahead and graph those two. And we want the right-hand intersection point here. So I'm going to use my intersect command. First curve, second curve. Set my guess out here to the right of that. And hey, how about that? They intersect at x equals 1. That was kind of nice. I probably could have and should have done that by hand. So we'll put that intersection point in there. And now in order to find the actual volume, I'm just going to go ahead and do this numerically on my calculator. So I'm going to quit out of here, and I've got pi times the integral of 6 squared minus quantity negative x plus 4 squared with respect to x from negative 2 to 1 plus pi times the integral of 6 squared minus quantity x squared plus 2 squared with respect to x from 1 to 2. And I'll go ahead and calculate that. And I get 193.103 for the volume of this solid. And that ends our lesson on solids of revolution of the washer type.